All right, hey class. Want to quickly cover one thing. We're kind of winding down some of the stuff we're going to talk about with circular motion. But one thing that we demonstrated was these kind of things, where the demo I did in class, where I spun a bucket in a vertical circle, and semi-surprisingly, the water did not fall out. So I want to break that down a little bit here. So you see this guy here, and let's see if we can draw here. We spun this around in a vertical circle, and fun for us is that the water in the bottom here did not fall out. Now, a couple things is that if you are in a situation like this, or if you were riding in this bucket, say if you were a jet fighter pilot flying in a circle like that, or if you were at the bottom of this bucket and you were stuck to about it, where is the water heavier? Where would you be heavier? At the bottom or at the top? And with a little bit of thought, it's a little bit like what it would feel like on a roller coaster, is that you're going to feel heavier on the bottom, okay? You're going to feel a lot more weight here at the bottom than you do here, okay? Meaning that if you're a jet fighter pilot, say in a situation like this, where you're going around in a circle like that, you are going to feel heavier here than you do downwards up here. Make this here a little bit bigger to indicate that. Now, why that is because, since you're going in a circle, you have, gravity acting on you, but you need centripetal force. And the net force towards the center is going to be your centripetal force. So in these cases, and we can assume that there's no linear accelerations, is that the net force is the net centripetal force. Those two things are kind of synonymous. Okay, so then the centripetal force, that's it. Anytime we find a centripetal force, that's the net centripetal force. Now, when we're at the top, over here, gravity is centripetal. It's pointed toward the center, so it's helping us out. The object's actual weight is helping us out. But remember, the actual weight is not how heavy you feel. The normal force. Now, in this case, the normal force is that force from the pilot's seat, pushing them upwards. Same as the force from the floor holding you upwards. So here, the force of gravity and the normal force are teaming up to make this. However, over here they are too, but the force of gravity is pointed away from the center, which means that the normal force needs to first overcome that, and then create all that centripetal force in the opposite direction. So this arrow down here is indicative of how heavy you feel at the bottom, whereas this one up here is how heavy you feel at the top. There are cases where you can feel totally weightless at the top. So you definitely feel heavier at the bottom. At the bottom, gravity is working against you. At the top, gravity is working with you, would be one way to think of it. Or maybe you want to look at it this way, is that the centripetal force, when we're at the top, is going to be a product of your normal force and the force of gravity. And both of those are going to be pointed in the downward direction. So we'll call them negative, and they team up to make a big negative centripetal force. The centripetal force at the bottom, though, you have the normal force plus the force of gravity again, but these two are in opposition. The force of gravity is still negative, but this is positive. And we need a positive centripetal force because what direction is the center of the circle at the bottom? It's upward in positive direction. So the fact that this is negative means that this has to be a higher positive number. Okay, so that answers that question. We feel heavier at the bottom, and again, if you try to simulate this, like on a roller coaster or something like that, that should not come as a surprise to you. Okay, so at the bottom here, this bucket, the bottom of this bucket is pushing this water inward. Okay, that's kind of the normal force. So the second question I want to ask you about this was, is there some minimum speed that this bucket needs to be moving at? Sorry about that. Is there some minimum speed that this bucket needs to be moving at so that the water does not fall out? or if you were riding in a ride or something like this, so that you stay stuck to your seat and you don't fall out. And yes, of course there is. And that happens when the bottom does not have to push at you at all. That happens when the force of gravity, which is downward at the top, is equal to the centripetal force that is needed. Okay? If we need more centripetal force than that, that can be provided by the normal force, but this would mean the minimum amount. So how could we figure that? Okay, if we know our equation for the force of gravity, that's mg is equal to mvt squared over r. That's our equation for centripetal force that I gave you. You have a mass on both sides of that, so those can cancel out. And solving that for Vt, you very simply get square root of r times g. And that's all that means, is that the minimum speed. You can go faster than that, and the water will still be stuck, because the force of gravity can be kind of supplemented by a normal force. But when there is no normal force, that is the minimum speed that we must go. Because if the centripetal force needed for a certain speed winds up being lower, the minimum centripetal force needed winds up being lower than the force of gravity, the object's going to fall out. The water, the person, the rider, whatever that may be. So this is an equation that tells us the minimum speed. You can set that by saying Fg at the top is equal to the force of the centripetal force. You can go faster than this, and the normal force or a tension force will help you out. And usually if I'm doing this demonstration, I'm certainly not going to be going at the minimum amount where it just barely gets up there and then can't quite make it. You're going to go fast enough to make sure that you are covered even if something goes wrong or whatever. In that case, obviously there's more normal force involved. Okay, so in a vertical circle, where do you feel heavy? At the bottom is where you feel heavy. If you stay stuck to your seat to achieve this water not flying out of the bucket demo, how do we know what minimum speed it must be? That's when the downward weight of the water is equal to the centripetal force. This all has to do with what's going on at the top. And solve that equation, it's just really simple, square root of r times g. Okay, so if you guys want to go to your packets right now that I passed out to you, if you did not get one of these, I will attach it to the assignment that I'm posting all of this with. And if you in that packet, at the front of it says speed and velocity, and then kind of in the top left it says circular and satellite motion. And I want you guys to go to page 9 of that packet. And again, I will attach it. This will be attached to the assignment as well. Alright, so we are on page 9 here. Just shrink that down so it all showed up here. Keep that stuck up there. Looking at page 9 on our packets. All right, I'm going to do number 1 for you here, and I guess this doesn't fully say, but if you're looking, this is your number 1 on page 9, and all of these are number 1. So parts A, B, C, and D. This is the only number on page 9. So we have a couple problems like that. I'm going to do problem A and B with you, and then give you guys a homework assignment to move on from there with. So it says a bucket of water with a mass of 2 kilograms attached to an 8-meter long string and spun in a vertical circle. The speed of the water at the top of the circular path is 3 meters per second. Now it asks us to find a whole bunch of things. So we are here at the top of a vertical circle. It looks like that. Okay, so let's figure out what they're asking. First, the force of gravity. Force of gravity is always just going to be m times g. So our mass of 2 kilograms times 9.8, so that's 19.6 newtons. Okay, that's an easy one. Then if we move down here to F net, Now that is the net centripetal force. The easiest way to explain it, like that means the same thing as the centripetal force. So for the net force needs to be the centripetal force. So centripetal force, we have an equation for mvt squared over r. M is 2, vt is 3. We square that's 9. So we wind up with 18 divided by 0.8, which gives us a centripetal force of 22.5 newtons. Okay, so we can write that in there. So that is the total amount of center-seeking force we need. And it's, of course, directed towards the center, because that's where the center of the circle is. And remember, wherever force is going, wherever the net force is going, that is also where the acceleration is going. So, the next on this list, we're going to figure out that tension. Now, we're at the top of a circle. Gravity is helping us get this net force. But not all of it. Okay, we need 22.5. But gravity is only giving us 19.6. So where is the rest of that coming from? That's coming from the tension. You can call it the normal force if you want, but basically the force of that bottom of the bucket pushing the water inward. So remember that centripetal force is also the net force, and that's going to be the sum of your gravity plus your tension force in the string there. So those two need to sum up to 22.5. Gravity gives us 19.5 of that, and Ft needs to make up the difference, which we do 22.5 minus 19.5. What does that give us? Minus 19.6, excuse me. That gives you 2.9 newtons of tension. So again, that tension, if you're writing in that, that's like the weight that you would feel, not how heavy you actually are. And then lastly, they ask for acceleration. And remember what acceleration means. Erase some of this so we got some more space here. That's your centripetal acceleration. Your centripetal acceleration, that also has an equation. It's the same as the centripetal force equation, minus the m, just vt squared over r. So vt squared is 9, r is 0.8. So 9 divided by 0.8 is 11.25, which is a little over 1 g. 0.25 meters per second squared. And so those are our answers for our whole first problem here. Okay? The net force is referring to the net centripetal force. The two forces that might be pointed towards the center are the force of gravity and the force of tension. Clean some of this up here, and we can go on to part 2, or part B. Okay, so we have all of our answers in here. If we go to part B, now instead of being at the top of the circle, we're at the bottom of the circle. We're swinging at the bottom. So if you notice now, gravity is still downward, but downward isn't towards the center of the circle anymore. Downward is away from the center of the circle. So gravity is still going to be mg, and it's still going to be downward. But what has changed, 19.6, is that downward is no longer towards the center of the circle. The center of the circle is up here for this problem. On this problem down here, the center of the circle was down here. Okay, so we're going to have to first overcome that and create a big upward force in order to get the centripetal force we need. So remember, the net force is the net centripetal force. So we need to figure out how much centripetal force we need in order to do this. mvt squared over r, m is 2, vt is 6. It's a lot faster now, and the radius is still 0.8. So 6 squared is 36, times your mass of 2 is 72, and then divide that by your radius, 0.8. That gives us a centripetal force of a very large 90 newtons. We need 90 newtons of centripetal force. And our force of gravity is actually going against that. Okay, that's going in the opposite direction. So, we need 90, and gravity and the tension force are trying to get us there, but gravity's going in the wrong direction. This is a positive force, whereas this is a negative. So this is going to have to be a really big positive force. Okay, so positive 90 is equal to negative 19.6 plus Ft. So solve that for Ft, and you get 109.6 newtons. Now, it's so much more in part B than it is in part A for two reasons. One, we're at the bottom of the circle, and so you're working against gravity rather than with it. And also because our speed is a lot higher, and because speed is getting squared in this equation, then obviously if we double the speed, that's going to be a 4 times greater amount of centripetal force needed. Okay, so fill in what we already did. We said 90 newtons was the amount of centripetal force we needed. That must be pointed upward, as does the centripetal acceleration need to be. And the tension force, again, 109.6. And then lastly, we have to find the centripetal acceleration. Centripetal acceleration is Vt squared over r. Vt is 6, you square that, that's 36 divided by 0.8. 36 divided by 0.8 is 45 meters per second squared, which is really fast. That's like close to 5 Gs of acceleration. Sorry, my writing on the screen is not super easy. Okay, so we did parts A and B. And again, we'll clean this up a little bit so you guys can just see our answers here. Alright, again, sorry for the bad handwriting, but I'm not used to writing on a screen very frequently. Okay, so that's the tension of the string pulling upward, gravity pulls downward. Again, and all this goes back to the different parts of a vertical circle. At the top, you have gravity plus tension working together. Here, gravity is working against you. So tension, or normal force, or whatever it might be, you can call it Fn if you want. And some problems they will. This is always going to be bigger. Okay? So what I want out of you guys, and I will write this on the heading for the assignment, is on the same page, I would like you guys to do parts C and D on page 9. So page 9, on your own, do parts C and D. And the same kind of page continues on page 10. So page 10, 2 problems there, E and F. And lastly, I would like you to do on page 11 this number 2. You can take a picture of that and attach it to where you turn in the assignment on Google Classroom. Please make sure you do all of that. If you have questions, always feel free to email me with whatever those questions might be. I know we're all kind of getting used to the whole new setup, and I'm no exception to that. So, like I said, don't be shy. It's a little bit harder than the concept builder I gave you yesterday. But C and D and a lot of these are very similar to the things that we talked about today. These are obviously questions that come from Physics Classroom, so if you want to, you can refer to the circular motion section on Physics Classroom as well, and they kind of explain some of this as well. Again, that's physicsclassroom.com. They give you some good extra help there too, especially since we don't really use a textbook very much in this class. That is tonight's homework assignment. I will post the due date and time for that. Please make sure you get that done. Hope you guys are staying healthy and following all the guidelines of the school and the state and the federal government and all that kind of stuff too. These are weird times. We are winding down the circular motion stuff. There's only a couple more things I want to talk about: bank turns and a couple other problem types. But we'll chip away at it and knock this out, and we'll wind up eventually kind of doing some kind of assessment on it. Again, email me if you have questions. If not, get all your homework done. Make sure you're staying on top of things.